Okay, I think something positive is happening there. Now, let me go in. I should have gone the other direction with this, but it's too late now. There is Blackboard. There's that. Okay. Looks like I might have gotten in. Well, it's going to be a good day. Okay, and there's the fluids class. Okay, let's see. Go there. Hopefully, it will have left off about where I hope it left off. And I know where I'm at. Okay, click an energy and movement. Oh, okay. Hey. Oh, wow. That's interesting. Just jump down to that. That's okay. That looks like a good problem to me. Matter of fact, maybe I'll assign that one, but then I'll do it real quick if I can figure out how to. Can I? Okay. Okay, usually I have a scrolling mouse, but I do not have a scroll. Well, I think what I'll do is I'll just copy it. That's what I'll do. Okay. So you know what? I'll just do this one, and this will be the. I want to. Okay. So I got enough information. I got that the water is ejected at B with that speed right there. Oh, I didn't get the question. But you know what? I'll go back and look and see what the question is, and we'll okay, okay, yeah. Just determine the pressure at A at the velocity. Oh, okay. Wait, determine the pipe assembly is mounted vertically. Determine the pressure. And that's it. Okay, that's easy enough. So know the pressure at A. Okay. I don't think I need the other stuff right now. So he's got A right here, and he's got B. So best thing to do, I I kind of like to do them like so. And there's a reason I like. So there are 4 or 5 different. Well, okay. So usually there's 2 ways. This guy actually uses a third way, and so let me write them all 3 ways, and I'll tell you why I like them this way. So the other thing you can see is PA plus gamma ZA plus rho ZA squared over 2. That's one of them. What did I just do with that? Oh, here it is. And then there's another way that the third way is something that he has decided to do. And it's okay, but what he's done is he's divided by rho. Okay, and it's okay, but you have to realize this is rho GZ. So if you divide that by rho, you get that. Okay, so let me just replace that. And then if you do that, you get V squared over 2. Now, he has used all 3 of these, and I'll tell you the justification for each one while I'm doing this. This one is loved by civil engineers, and because its units of the equations are in feet of water. And the beauty there is a civil engineer may walk out onto a piece of property sees a lake and sees some hills, and and also he may go in his office and see a contour map. Here's the contour map of a piece of property, and he knows he's going to have like a hole down here, so water's going to flow downhill. So a civil engineer will look right here and look over at the side of the hill and says, "Oh, you got to pump up over this pipe." Well, how high is that? Well, that's 100 feet. So he can immediately relate things to this equation because visually he can see it. He can see that. He can also see it on the contour map. And so the other beauty of this thing, hang on, let me get rid of everything, is later it turns out, oh, I'm sorry, I reneged. This is the civil engineer, and this is in units of feet. So that's the one the civil likes. But the beauty of this one over all the others is the loss equation that we'll see. Okay, the other book is in chapter 8, but it still might be in chapter 8 here. I don't know. Maybe it's chapter 9. But it's a very important part, and the loss becomes FL over D, V squared over 2G. And the units of this are in feet or in meters. And this loss equation is what you use to figure out what the real loss is. If he's pumping his water up the hill, through a certain type of pipe, you're going to have some losses occurring because of that. And it turns out that's the equation you use. You can easily adjust that equation to fit the others, but that's how it's presented to you. This one is loved by mechanicals and aeros. Because PSI is a common thing, airplane, when they say, well, what's the lift, of the airplane? Well, here's a wing, and I have so many PSI down here, so many on the top, and the whole area is so many inches squared. So you can figure out the lift like that. So aeros and mechanicals will live in this PSI world more. Plus, we're in, we were in thermo at one point, and in thermo, everything is PSI or, pascals or something like that. So we live there, but a civil engineer now, in the old days, they did take thermo, but I don't know that the civils do take thermo anymore. I'm not sure of that. So if I'm speaking out of turn, this one, I just don't know what to think about that. Because it's in feet squared per second squared. So I really, when he's presenting this in here, to me, I look at that and I'm saying, why? That doesn't fit a civil or a mechanical. But it doesn't matter, because if you know the numbers, you put them in, you're going to get the same answers. Everything will be fine. So you can do any one of these on this problem. More than likely, I'm going to do, I'm a mechanical, but because of the course, I'd just go to this, because I know eventually, if you were considering losses, you would do this. F L over D, V squared over 2G is equal to PB over gamma plus ZB plus VB squared over 2G. Does that all fit on there? I guess it does. So in essence, you start with your energy at state 1. State A, right down here. Then in the process of this water going through this pipe, maybe the pipe is really rough and loses a lot of energy, but it loses that energy. And that is a term that will, this is the length of pipe here, and that's the diameter of the pipe, and this is the velocity through the pipe. So the only thing that's weird here is this F, and that's the whole point of a later chapter, is determine what that F is. And it's moderately accurate, depending on if you know all the pipe things and stuff. And this is your final energy state, or not final, but at B. So if you don't have losses, this term is gone, and you've got just this energy is equal to that energy. Now, legally, if your velocity, I mean, it makes sense if you stare at this for a minute. If your velocity is low, there's too many O's there. So low squared becomes even lower. Say V in the pipe is quite a bit less than 1, maybe 0.1. Then 0.1 squared, you're going to get a small thing. The other thing is if the length is really short, if this section, if the length from here to here is really, really short, you may find that the losses are not, or they can be neglected as well. And if you have a combination of both of those, this term can really be reduced down. But in essence, this is what the term we're going to look at later. So we're going to assume no losses. Let's see, there are 2 or 3 terms. Inviscid means no losses. No losses mean no losses. And both those mean that this term is basically 0 and that the energy in the 2 states is the same. So I like to do my little table. And then I know I have 3 terms, P, Z, and V. If I can work these terms out. One thing I know, this is coming out into atmosphere, so that's a B, and that's going to be nothing. If I make this datum, then ZA is going to be nothing. And this is going to be 1.2 meters. Looks like we're moving in SI right now. V at B, he said, was 0.75. So voila, I know everything there. I can actually figure out everything at B. What do I not know at A? And what I don't know is, here, let's try that. Oh yeah, because then I'll get my pins. What I don't know is I don't know that one, and I don't know that one. But one of the things I do have is I have continuity, which can take me from this one to that one, because I have a diameter here and I have a diameter there. And I'm assuming those are diameters. I have no other, showers are usually, and pipes are usually round. If they're different, they should tell me they're different. So using continuity first, I'll basically go from A to B. And what I'll do is area at A, there's too many A's in here. Velocity at A is equal to area at B, velocity at B. And so there you go. There's those two. And so the area at A, where's A? So that's pi. And I'm not even going to worry about, you know what? I won't even worry about dealing with that. BA, which I don't know A, right? I know B, equals to pi 200 squared over 4 VB, but I can insert the value for VB. Yeah, so then I can sort of get rid of that, and then I can say VA equal 0.75, 200 over 80, or to 20 over 8 squared. What is that number? I'm sorry. And I have to really apologize about the lectures I did when I was sick, because I was coughing. And I listened back at them, and I put my hand on the microphone. I thought I covered it. So if I coughed in your ear, I'm sorry. Yeah. That's the answer? 2.25. Let me. Oh. Oh. Okay. Sorry. 4.68. That seems reasonable. So that's the velocity from continuity. And now that I got that, I kind of want to get it over to the side. So I'm going to put it over here. And then just because I want to signify that it is different, I'm going to just sort of put a green box around it and say that was my continuity that I used. Um, then I'll go back to this problem. And so what I'll do a combination of these things. So what I'm going to do is kind of, you know what? Here's what I'll do. I'll drag this thing down here because I was doing, oh no, it was doing that to me the last hour where it would, usually I could hold the pen down. Oh, now I got to put the keyboard on there. Okay. Okay, hello. Oh, there we go. Control C, and I'll drop it right there. Here, drop it right there. And then what I'll do, I'll go over and get this and copy this one. And I'll do a Control C, and I'll put that one right about here. And then I'll say they're equal. And then what I'll do is I'll monkey with everything according to this chart. Yeah, exactly. So I can actually put that in now. I could take 4.68 and I could put that in now. 4.68, and that's from continuity. And that's how these two are related. And that's a very common thing. If there's a continuity issue, like if you had a C and a D and an E, new points in there that he's asking questions about, you could actually, if you knew the diameters, you could fill out all of these. And then you may have you would have to know physically where they're located. Then the only thing you'd have left is the pressure. You could find the pressure anywhere along here. And so essentially, the continuity is very beneficial because it'll basically, you can just fill out this relationship all up and down this column here. Just basically, it's pretty beneficial that way. I wonder if I could use a green one. There you go. I want a green here. So, sort of looking over here, ZA. I know that one's going to be 0. PA. That's one of the ones I'm looking for. So PA over gamma plus 0. What is VA? VA is 4.68 squared over 2 times G, and I'll fill in G later. Pressure at B, woo, that's good, 0. That is B, that's 1.2. So 0 plus 1.2 plus VB, which is that one, 0.75 squared over 2G. Now, I have G is equal to 9.81 because I'm in SI. And gamma in here is 9810. And that is, okay, well, I like to think that this is kilograms per meter to the third. And this is nothing more than G times rho, which is this number, and that number. And those two numbers go together and give you the 9810, and it's in newtons. I better not put the T. I have a bad habit of putting the T after the newton per meter to the third. So what I've got is pressure A over 9810. In the book, sometimes he'll have 9800, and I guess that's okay. Plus 4.68 squared over 2 times 9.1 equal to 1.2, and then you get this 0.75 squared, which is kind of a small number, but 9.81 And so then you just get pressure A equal to 9810 times, well, shoot, okay, 1.2 plus 0.75 squared over 2 times 981. And then you got to minus the 4.68 squared over 2, 9.81. Did I get that right? Let's see. Velocity is going to be, oh, I forgot to put the bracket. Velocity is going to be much faster through there. So probably there's going to be pulling tiny amount of a vacuum, maybe, depending on how, depending on this number. Depends a lot on that number. I don't know what that's going to be. Oh, man. Oh, I'm going to drink something real quick. All right. It's totally, did you get it yet? Okay. Yeah, while you're doing that, you'll know here. Other thing is different. Now, let's see. Did you get it? 11.05. Okay. Yeah, I don't really know the answer. That should be Newton's or Pascal or PA or something like that. Let's see if we can find a.
It was a little number minus another little number.
Oh, was it?
It was a little. Those were all little numbers.
Oh, okay.
And then it was 1.2 minus that.
So the 1.2 pretty much predominated over those two. Yeah. Maybe.
Well, it was a little number, and the other number was negative 1.11.
Oh, okay. I'm gonna try something really bizarre. I got this app on here, and it's supposed to. What? They're asking me questions. So it said, "How old are you?" So I said 99. That's funny. Let's see if it figures it out. Oh, oh boy, cool. I just took this thing and it calculated it for me. Oh, that is cool. So did you get something like 0.0889717 times 9810? Is that about what you got? That is slick.
I got 0.11 is what I got. Not saying that's right, I'm just
Well,
telling you
okay.
what I got.
Let me kind of let's see if I can let's cancel that one. I want to try to think, how do I cancel it? Okay. And then I'm gonna do this one. See if it calculates it for me. That's slick. I never, huh? 198.10. I think it. Oh, okay. It made a mistake. It interpreted this as a 4. Let me see if I can fix that. So, uh, interesting. That's cool. Now that I know how to do this, I'm just going to do this in class a lot of time. Yep, I got. Okay, so it says, oh, well, it goofed up again. It said this is a 3.
It did pick you about, is that photo map?
Yeah.
And it picked about handwriting.
Yep, that's it. Your answer is what it said. 9.0%. Yep, that's it. My daughter introduced me to this, and I didn't even think about this until just 5 seconds ago. And I'm like, hey, I wonder if this will do it. So, but at least it gives you it gives you all the equation numbers so you can look at it to make sure. So, yeah, it says show solving steps, but I mean, in this particular type of problem, it's just basically doing calculator work. Cool. I didn't think about even using that. I think I'm going to start using that, especially if you got something like this and you got a picture. You can just put it on the page, and if it interprets it, that's perfect. All right, that's cool. Okay, so let's see if I can. Is that what? That's it. That was it. There's really not anything else to find. Now, if he had said, okay, what's the pressure right here or the pressure here, we'd have some more things to calculate. But like I said, continuity will take us through these. And then the elevation, he's going to have to give us these in order to find those. You can't really very well say, find the pressure at point C, and it's somewhere between A and B. You got to know exactly where it's at. So, let's see if there's another problem that's kind of short-lived. I might just give you that one. I'm just going to give everybody one thing for this weekend because there may be a good chance there's a lot of other people out there with the flu. It's not fun, let me tell you. This is kind of a good one, but it may take a little longer than. Okay, so in order to determine the flow in a rectangular channel, a 0.2 foot bump is added on its bottom, on the bottom surface. If the measured depth of the flow at the bump is 3.3, determine the volumetric discharge. The flow hey, we should be able to do that one. I don't know if we can't complete it by the end of this period. We'll work on it next. We'll finish it next time. Let's get it over here. And we'll just put it right there. And hang on just a second. Okay. So he told us the bump height. And he told us the other thing. Okay. Gosh. This might be this is weird. Okay, so here we got A. We got B. If I went up 0.2 and then I went up 3.3, that should be 3.5, right? And so I'm going to take that as my datum. And I'll say, let me just go in here and do this. I'll say his A is A and the B is B, of course. PA over gamma plus ZA plus VA squared over 2G. Say we'll say there's no losses, so I'm not even going to write that thing. Plus ZB plus VB squared over 2G. Now, one of the things I do know, and this is kind of weird, but not that weird, but VA area A, I'm used to seeing 1, 2, and 3, and 4, not A, B, and C, and D for points in there, but that's okay. So what I've got is it has a uniform channel, and it says the channel width is 2 foot, but guess what? It doesn't really matter what width it is. So my area at A is essentially that times the 2 foot. I can make that 1 foot. It will not change the problem. So the area at A I'll take as 4 VA, and then the area at B will be 3.3 velocity of B. So then I'll relate the two. The other thing is I'll take that and the top. I'm taking the top points of the water, and then ZB, I'm setting my datum to be the elevation of the water at B. So that's that. And that means this has got to be a half of a foot above it. If I'm adding that right, 3.3 and 0.2 gives me that, and that's a half a foot below that. So I get a half a foot plus velocity A over 2, and I'll keep using G is equal to velocity of B, 2, and G. Now, I can sit there and take these two, and I can take 4 divided by 3 point, sorry, 4 divided by 3.3, 4 divided by 3.3, is that right? Yeah, 4 divided by 3.3, VA is equal to VB. And then I can just stick that in there. For that matter, you could reverse around and stick the other one in there. It doesn't really matter which one you find. Okay. That's 1.21. Oh, okay. So 1.212121 times V, A, and all that gets squared, and it's 2 and G. So my end result, the end thing I'm looking for is to find VA, because then he wants to know the volumetric discharge, which is why he gave you the 2 feet. But I'm just going to find the velocity and then multiply times the area later. So I'll take this thing over to there and add those two. So what is that? 0.5 equals to VA squared 2G. Now something's bothering me here. Did I do that backwards? And that's okay. Something's really bothering me. So I'll move that over. Okay, 1.21. And then it's 2, 1, and 2, like that. 1.21312121. Oh, why am I putting the 2G in there? Okay, how about that? Now, you know what I'll do? Okay, that's because I had this one that was the 1, and then it gets pulled over here, so it becomes minus VA squared over 2G. And so, okay, so now I got to take the 0.5. I'm going to use this photo math again. Times 2 times 32.2. And notice I'm writing it I'm trying to write it so that I can get a good picture of it. 1.21212 squared minus 1 Oh, and I need to take the square root of it. Let's see. I'm going to really push this photo math thing. Will it? All right. Here we go. They put it in that little box they've got for me. It did it. Well, I think it did it. Okay, wait. 0.5 times 2, 32 point. Yeah. 8.28386 is equal to VA. Now that's VA. Which one was A? A's back here. So the area at A is actually 4 by 2. And so the volumetric flow rate is the area at A times the velocity A, which is equal to 8 times 8.28386.
It doesn't like it.
Oh, it doesn't?
The 2 zeros, it doesn't like 25.
Oh, this one?
I don't know if it would take.
You think that one? Let's try it. Okay, here we go. Oh, look at that. It truncated. It dropped to 8.6. What? Divided by 6? No, that is not divided by. It thinks that's a divided by symbol. Huh? Now it's got 8 times that. That's weird. What is it doing? This is weird. This is bizarre. Okay, well anyway. 60, wait, 86? Sure. 66.27. I have no idea. I still don't understand why it can't get that. Okay, 8 times 8.28386. Let's see if it'll do it this time. We did it. What is it trying to do? It's wanting me to pay to get the plus version. I don't want to do that. Oh, and then you slide down and it has the whole thing. Okay. So it multiplies. Why does it not do this? It gives me it's 66 and 1. That is a weird answer. Okay, 66.27. Yeah. That's really strange. Yeah, but it put this little thing in the middle and it said animated tutorials for the plus. And then you have to slide down and it shows you the. So it's trying to get you to pay. I mean, that was beneficial. So, well, so that didn't take as long as I thought it would. So, I don't know. What do you think? We just call it a day. After this, okay, so Bernoulli's goes for a while. Actually, I don't know that it goes that much more at all. And then we do momentum. And then we do a little thing about non-dimensional numbers. And then we do Bernoulli with losses. And then I like to throw in a section about pumps. And then I guess we're done. So I'll just claim we're done. Just hit this and do stop streaming. And then it goes away.